Next, inter molecular distance. Intermolecular distance, right, is maximum, right? Got it. Here it is negligible, so I'll write it as minimum as well. Maximum as in it will try to occupy as much free space available as possible. That is the important property of gases. It has no shape, no shape or size, but it takes the shape of container, so in which the state of matter is present. So this is the basic idea you should know about gases. Within this, there is one very important assumption. That assumption comes with the fact that what type of a gas you are assuming to be. If I take something called an ideal gas, okay, ideal gas as in a gas where there are no interactions between the particles. So that is a prime importance in ideal gas. No interaction between the molecules or particles. Okay. Other important assumptions when it comes to when it comes to ideal gas is intermolecular distance is very large or maximum, very large, and because of which the volume occupied by container, sorry, volume occupied by gas, which will be normally written as volume of the container, and volume of the particle as compared to that of volume of the container is too small. So we will neglect the volume of particles. Right. So these are the basic assumptions which we observe. And most of the space is voids only. Most of the space in gaseous state, in ideal gas, is voids. Alright. Hence, since it is completely voids, it is highly compressible. Highly compressible. See, these are all the terms that have been asked in various competitive exams. So understand the terms carefully, guys. Finally, this brings to the fact that potential energy of an ideal gas is zero. Why? Because there are no interactions, so there is no attraction or repulsive forces between the particles, which tells us that there is no interaction. So, which gives us an idea that there is no potential energy between the particles. Lastly, if you see, gases will keep moving continuously, but in a random motion like this. But during this motion, they will only make straight line. They will move in straight lines. This type of a motion is called Brownian motion. Brownian motion. In fact, not just ideal gas, any form of a gas or liquids, they usually show Brownian motion. Okay. And gases will show pressure or exerts pressure on walls of the container. Walls of the container. How they are exerting pressure on the walls of the container? First, they will keep colliding with themselves, keep colliding with each other and with walls of the container. So these are few simple things you must learn from ideal gases. Okay, and all the classical laws are applicable here. Classical laws are applicable, which means Newton's first law, second law, whatever we will write about, all those are applicable. So that is about the ideal gases. Now, first I'm discussing all the terminologies so that once you are clear with the terms, it will be easy for us to learn each and every problem. Next term is about state and phase. State and phase. See, state of a gas, when we use the word state of a gas, it is the physical condition of matter, correct? So in this case, gas. It can be defined by state variables. The main state variables which defines the condition of a matter is pressure. We usually write it as P, volume, V, temperature, T, and number of moles, N. This will define what is the state of a gas. And a state can always be changed from one state to the other state. State 1 to state 2, like P1, V1, T1, N1 to P2, V2, T2, N2. Like that, we can change the gaseous state from one state to the other state. Let me just brief you about these terms here. When it comes to volume of gas, we always assume it has the volume of container. And container volume, when it comes to container volume, the units which we use are liters, decimeter cube, centimeter cube, meter cube, ml, and so on. Simple relation, if you just recall, 1 liter is 1000 centimeter cube, which is same as 1000 ml, which is same as 10 raised to power of minus 3 meter cube, or same as 1 decimeter cube. You can relate one another based on that. Similarly, when it comes to temperature, basically it is a measure of heat content. How much is the uh, heat content present in the system? Heat content. Or the other way of defining it is degree of hotness or coldness. Degree of hotness or coldness. It can be defined in Kelvin scale, or degree Celsius scale, or degree Fahrenheit scale. The way they are related is Kelvin scale is equal to degree centigrade plus 273.15, and degree Fahrenheit is 9 by 5 times of temperature in degree centigrade plus 32. Okay. So this is the next important term you must learn about. What are the state functions? What are their units? How they are related with one another. Next, when it comes to containers where the gases are present, these gases can be present in different types of containers where you have different walls. And these walls are also of two kinds. One is diathermic. Suppose there are some gases here, there are some gases here. So the walls could be diathermic wall, or it could be adiabatic wall. Adiabatic or isolated is same. So diathermic wall allows heat allowed. Okay, so it will flow of heat is allowed. So heat flow is allowed with this wall. Then we call it as a diathermic wall. If heat flow is not allowed, like in the case of thermos, so heat can't flow out or come into the system, so no flow of heat allowed. So those are called adiabatic or isolated walls. Okay. So usually, if this is maintained at temperature T1 and this is maintained at temperature T2, for instance, this gas is maintained at temperature T1 and T2. If T1 is greater than T2, we will see the net heat flow will be from T1 to T2. Very important during problem solving. So both sides heat is flowing. Considering this is diathermic wall, then if T1 is greater than T2, net heat flow will be from T1 to T2. If T2 is greater than T1, net heat flow from T2 to T1. And if T2 is same as T1 or T1 is same as T2, no net heat flow. No net heat flow. See, heat is flowing, but the total heat that is flowing from left to right and right to left is same. This is called a state of thermal equilibrium. Thermal equilibrium. And whenever we talk about gaseous state, we always consider that it is under thermal equilibrium, which means if you say this particular side, temperature at each and every point in this particular volume is same. Temperature in this side is also at same temperature. So with respect to the system, if this is a container A and this is container B, with respect to A, within A, it is at thermal equilibrium. Within B, it is at thermal equilibrium. Now, if A and B has to be thermal equilibrium, then the net heat flow should be 0. I hope you guys understood that. Then we use this word thermal equilibrium. And most of the gas laws which we will study, we always see at thermal equilibrium only. So this is about volume and pressure. So far, any doubts, students?
No, sir.
Okay. The last important term is pressure. Okay. It's pretty much easy to calculate the pressure of a solid substance, because if it is a solid substance, I know how much amount of force that this is been acting. From that, I can calculate pressure, which is force by area. I can easily calculate the surface area. So for solids as well as for liquids, the same thing I can do it for liquids also. So I can calculate pressure is equal to F by A very easily. But in the case of gas, it becomes difficult. Reason being, the pressure acted in all the directions is same. Secondly, no influence of gravity. No influence of gravity. So it's not like gas particles are attracted towards gravity. Therefore, it becomes slightly difficult to measure the pressure. Okay. In fact, if you want to calculate the pressure, then we have to know how much is the force that is acting. So theoretically, how do we calculate? So force will be equal, pressure will be equal to force by unit area, where force is defined in newtons, area is in meter square. So the units will be Newton per meter square or pascals. Okay, this is the unit we generally use in SI system. And how do we calculate the force? So if this is a wall of the container and a particle is coming and hitting here with a linear momentum mv, after the collision it will come back with same mv because there is no loss of energy here. So the change in momentum delta mv, right, this change in momentum per unit time is what is defined as force, and that force divided by A gives us pressure. Okay, so that's how theoretically you can calculate the pressure, but practically we need to know how to calculate as well. Okay, just like how we have thermal equilibrium when temperature on both the sides becomes same or net heat flow becomes same, similarly if the two gases are at different pressures, let's say this is gas A connected to gas B, and both of them are maintained at different pressures, and here if this is a wall which is movable wall, right, in that case there is certain amount of pressure this is acting, certain amount of pressure this is also acting. Okay, so if pressure P1 is greater than P2, okay, wall moves towards right, and if pressure P1 is less than P2, then wall moves towards left, right? And if P1 is equal to P2, no motion of wall, no movement of wall, right? And we call this state as mechanical equilibrium. Mechanical equilibrium. All right. So when the pressure between the systems within the system is same, then we call it as it exists in mechanical equilibrium. So one thing we have learned, what is thermal equilibrium, what is mechanical equilibrium. Next we learned what are the parameters. Calculating volume and temperature was very easy, but calculating pressure was a challenge. So to calculate the pressure, right, which we call it as the measurement of pressure, we need separate tools to do that. The main tools which are used are barometer and manometer. Barometer and manometer. Now to understand this, first we have to learn something called pressure in a liquid column.
Sir,
Yes, beta.
sir, why are we studying ideal gases if they don't exist?
Okay. The general way of studying physics is we take the least amount of variables. Please understand the psychology. We take the
Yes,
least
sir.
amount of variables and we will improvise and add multiple variables into it. Is this clear? For
Yes.
example, when you study physics, especially mechanics, you study with force, correct?
Yes.
Usually start with force. Are you considering air force? Are you taking any frictional force? Are you taking any sound waves?
No.
You are ignoring all of that, right? You are trying
Yes.
to go with the minimum number of variables. That is just a mass, correct? A particular mass, a constant mass which is present, and a simple acceleration. From there, you will start writing F is equal to ma. Then, as you go towards the chapter, what you have seen, slowly you will add friction first. Slowly you will add rotation, correct? Slowly you would add air friction. Slowly you will add fluid friction. Slowly you would add viscosity. Are you getting it? That's how the chapters are developed.
Yes.
Understood? Same way.
Okay.
To learn gases also, first you need to start with ideal gas, then you will get into the real gases. Okay.
Okay, got it.
Suppose if at all I have any particular liquid in this, this is a simple liquid column, and this liquid column is at a height h. At this point, observe this point carefully. I'll call this as point O. At this point, can I say the total mass of the liquid multiplied by gravity is the force that acts on that? So therefore, if density of liquid is rho and area of cross section of this cylindrical liquid column is A, and volume of liquid present in it will be A into h, where h is the height. Then what will be the mass of liquid present in it? It will be rho into volume, which is equal to rho into A into h. So this is the mass of the liquid which is present in it. And what is the force acting on that point O? Force on point O would be equal to mass into G, which is rho into A into h into G. Okay. And what would be the pressure now? Pressure would be equal to force divided by cross-sectional area. So that area term will get cancelled. We will get this as rho GH. So this is the same formula you will be using in physics and chemistry as well. That I hope now you understood how it is derived. So the pressure is rho into G into H, where rho is the Density of the liquid, g is the acceleration due to gravity, and h is the height of the column. So from here we are supposed to calculate the pressure. Now suppose this was pretty simple. In case if you have that column which I kept is vertically up, what if the same column is tilted with an angle theta? So same liquid is present here inside, and this time I'm trying to calculate what will be the pressure at this point O. This is the same point O. Now gravity will only act downwards. So if at this point gravity is acting here, G, then it will have two vectors. This will be G cos theta and this will be G sin theta. Yes or no? I hope all of you are able to follow this. This side we will have G sin theta. Rest all is same. Cross-sectional area is same. Density is same. There is no change in it. So the pressure exerted on this point now is only based upon the sign component of gravity. So therefore, pressure will be equal to rho g h sin theta. I hope you guys can observe that. So if this is theta, you know this is also theta, right? So if that is theta, then this will be g sin theta. Clear, guys? Any doubt here? Okay, so in generic, when you're writing, this will be the formula for pressure of a column. If theta becomes 90 degrees, then this is the case. So that will become sine theta, sine 90 is 1. So P will become rho g h. Okay, boys. Next. Once you know the column pressure, now we can read what is barometer. So in barometer, what we are doing, we are taking a trough, got it, a bowl here, in which we are filling the mercury up to the brim here, and then we are inserting a column. We are inserting a column here, a small capillary column here, and it is closed on one end, and it is vacuum inside. It has vacuum inside. So when we do this here like this, now what would happen on this surface? On this surface, if you expose this to atmosphere, in case if we expose this to atmosphere, what would happen? On the surface, we will see there is a pressure acted by the atmospheric air which is present. So let's say the pressure exerted by the atmosphere, I'll call it as PATM. And because of this pressure only, there will be rise in the column here. And it will rise to a certain height and stop here, which means it has reached the mechanical equilibrium. So at this equilibrium, the pressure exerted by this gas, that is outside pressure, will be same as the column pressure. So H is the mercury height column. H is the height of Hg column. So from here I can say that pressure exerted by that atmosphere would be equal to rho into G into H. This is what you will expect. Okay. I think all of you understood that, right? Now this pressure which you calculate in SI units, you can see that usually we take rho as kg per meter cube, G as meter per second square. Okay. Next, H we take it as meters. So if you put all of them, we will get pressure as Newton per meter square, which we call it as Pascal. Okay. The generally when you take our air around us, around in our atmosphere on over the surface of the earth, the pressure exerted is approximately 1.013 into 10 raised to power of 5 pascals. This much of pressure is being exerted by air approximately. Okay, this may not be precise at each and every location because we have different topographies on Earth, but this is taken as a standard average. On this, if you observe, this, instead of using the term 10 raised to power of 5 and 1.013 always, we have designated this as 1 atm pressure. This we have designated as 1 atm pressure. So when we say 1 atm pressure, it is equivalent to these many pascals. The other way is 1 atm pressure is also referred to be as 76 centimeter rise of mercury, right? Because this pressure you will get when the column height that is raised is around 76 centimeters. In here, the density of mercury is 13.6 gram per ml. This is the density of mercury. So in this case, we will get this certain pressure. Okay. The question that would be asked is like, why we are only using mercury? The reason is it has high pressure. Instead of mercury, if we take water, it will become a simple question now, correct? I can use that as a question here. Find the height of, okay, water column. Find the height of water column if it creates, if an equivalent pressure of 76 centimeter Hg is applied on water. Okay, beta. So in this case, if the same pressure is applied, P rho 1 G H1 should be equal to rho 2 G H2. So where H2 is height of the water, let's say, that should be equal to rho 1 into H1 divided by rho 2. So rho 1, which is the density of mercury, is 13.6 into H1, which is 76 centimeters, divided by rho 2, which is 1 gram per ml, right? Density of water is approximately 1 gram per ml. So when you do this, approximately you're getting 1033 centimeter, which is almost as close at 10 meters. So which means it is highly impractical to use water, because if you use water, because of its low density, we need to have very big columns to be maintained. Okay, that's why mercury is used, which is a highly dense liquid. I think all of you understood this point. So this is about barometer. The other units which we will be seeing for pressure or bar, 1 bar is equivalent to 1.013 atm. Got it? Okay, sorry, the other way. 1 atm is equal to 1.013 bar, and 1 atm is also represented as 760 centimeters of mercury or 760 torr. The first barometer was made by Torricelli, so this unit was named after him as 760 torr, which is same as millimeter, sorry, 760 millimeter. I hope you understood the barometer part. Similarly, if you want to calculate the pressure of an individual gas, we can use something called manometer. Manometer would look something like this, a U-shaped tube where we have filled mercury in it. And on one side, we have individual gas. This part we have closed with a rubber cork, and one side we have exposed this to ATM, atmospheric pressure. Due to atmospheric pressure, what would happen? Here, due to atmospheric pressure, we can find out that this height in the column will change. So the height might increase to this point like this here, and it will decrease to this point here. So something like this will happen. So this new height which has made here, that is the resultant of this pressure, that is resultant of this pressure and pressure due to gas. So pressure of the gas, got it, uh, is equal to pressure because of atmosphere minus rho gh. So that is the resultant pressure which you will get. What if the pressure of the gas is more? If the gas pressure is more, then that will compensate to that of ATM plus rho gh. And here now the column height will decrease here, column height will increase on the other side. So the general way of writing here for manometer, the formula is P gas is equal to P ATM plus or minus rho gh. So this is the general formula. So the instrument used is manometer. So I hope you guys understood this, what exactly is happening in manometer. Okay. One interesting fact, when you do the questions, you need to understand this. Suppose if this is the mercury column, mercury bowl or container. Suppose if the pressure act at this point is at this point B, and if you consider at point A, correct? There is some liquid present here, let's say. Here there is some liquid present, correct? And because of that liquid, it has maintained in the height h. This is point B. See, the pressure acting at point A will always be equal to pressure acting at point B because they are at mechanical equilibrium. Please understand that. That would become an important criteria. Okay. But suppose if you have uh, some gas present inside, let's say on the same column, at this pressure, at this point, there is a mercury as well as some gas present here, some extra gas which is present here that got stuck inside, and this is at height h. This is the same point B and A. In this case, what would happen? Pressure of A, pressure acting at A will be equal to pressure acting at B, but this pressure of B is because of both rho gh and pressure of gas. But here in the first case, pressure of A is only pressure of B, which is rho gh. So these type of barometers are called perfect barometers. Okay, or these type of barometers are called faulty barometers. Faulty barometers. You would be in JEE, faulty barometer cases have been asked where there is some gas being stuck. Then how do we calculate the pressure? Right. So this is the kind of questions that usually come in JEE, at least from this area. I hope you guys understood that. Okay. Now one typical question that comes from this area, especially from the column pressures, is when a column is being kept on a particular surface, a horizontal surface here, and let's say there is some mercury column which is there here, and there is some gas stuck in it, P gas. The height of this column, let us say, take this as 8 centimeters, got it? And this height originally is 10 centimeters. This is how originally it is. And from this end, from outside, there is an ATM pressure acting. This is originally how it is. Now the question asked would be, calculate the pressure if tube is kept vertically up, vertically open and up, or tube is kept vertically open and down. Second question. Third question is tube is kept at an angle of 45 degrees inclined with horizontal. So such type of questions are asked in JEE, and this has been already asked once or twice in JEE, where initial data is given. You have to find out what will be the pressure in all these three cases. Okay. You can express the answer in terms of centimeters of mercury, because here pressure is 76 centimeters of mercury, because atmospheric pressure on in a standard we always take it as 76 centimeters of mercury. So guys, you can do that. Please finish that. Any answers for the first one? Ansh, Arnav, Harya, anyone?
Sir, one second.
Arnav, is that the change beta?
I have to give you the change or the column height.
I want only pressure, okay, not column height.
Okay, you want pressure. Okay.
Column height is the next case which we will learn it. Right, once I decide the Boyle's law, I will come back to the same question and help you out. Here just we'll find out first in terms of pressure. Right, Ansh? So as of now, X is not something I wanted to calculate because I don't know what is Boyle's law yet, correct? Now here, basically pressure of gas, if you check out, those who haven't understood, don't worry, just check out the solution. Those who have understood, just finish up the three parts of it. So here the pressure is what I'm checking out. The pressure is acting because of, from top there is an atmospheric pressure acting, and at this point the column pressure of 10 centimeters will also act. This 10 centimeter column pressure will act. So the pressure of the gas would be simply pressure of ATM plus 10 centimeters pressure. And pressure of ATM, when I represent in terms of mercury, it is 76. So 76 plus 10. So how much? It is simply 86. Okay. So the pressure of gas which it experiences is 86. B part, if it is vertically pointing it down here like this time on this point, if you check out on this point, if you check out what is the pressure that is acting from here, there is ATM atmospheric pressure acting, but down there is a pressure which is acting, which is mercury pressure, and from the top it is the gas pressure which is acting. So the gas pressure plus mercury pressure is balancing the atmospheric pressure. So which means gas pressure will be equal to 76 minus 8. Okay. So that would be 68 centimeters. Third part, we know that pressure of gas, now this is slanted with an angle theta, and there is a gas inside. So you can see pressure of gas acting from this end. So this is pressure of gas, mercury is acting this end, and pressure of atom is acting from this end. So pressure of gas is being balanced by pressure because of mercury and pressure because of atom. Pressure because of mercury, only the sign component will act. So therefore, it would be 8 sine theta plus how much is the ATM? 76. So 76 plus 8 into 1 by root 2. Uh, 8 centimeters, no beta. 84, sorry. I took 10 centimeters. Thank you. It's 8 centimeters, so 84 centimeters. Yeah. Okay, Ranveer, is this clear, everyone? Okay, this is one type of a question that is asked. Now, going ahead, so we learned what are the state functions. Let me keep repeating. We learned what is ideal gas. We learned to define ideal gas, we need state functions. So we studied pressure, volume, temperature. We also learned how to calculate the pressure of gases. Now we can dig into the idea of how to relate pressure, volume, temperature, and number of moles using gas laws. So using gas laws, we are trying to relate them with one another. First of the relation that was found is by Boyle's law. Boyle's law tells us that at constant temperature and for fixed number of moles, pressure will always be inversely proportional to volume. This is what has been observed. Okay. So which means if I take pressure P, that would be equal to some constant divided by V. Okay. Which can be evident. Suppose if you take a small syringe, okay, small syringe like this, a plastic syringe. Usually in a plastic syringe, first we will have a piston here inside from which you can press it, right? This is the way it looks like. Imagine initially there is some pressure P1 and volume V1, and I'm holding this end with the thumb and I'm trying to compress this. After compression, let's say the movement has come to this point. So now the new pressure is P2 and volume is V2. See, temperature has not changed, neither I have heated or anything. Neither I have released any moles here. The gas is intact. It was not moving out of that system. So the number of moles are constant. So in this type of system where temperature is constant, number of moles are constant, I can relate pressure as inversely proportional to volume, which you will experience now. As the volume decreases, you can experience the more pressure acting on your thumb. Okay. So which means pressure has increased. So volume decreases, pressure increases. That's how it is related. Or I can say P1 V1 is equal to P2 V2. Got it? Now, generally, when you have pressure versus volume graph, pressure versus volume, if you are plotting, you can see it is like PV is equal to some constant. PV is equal to some constant is like X into Y is equal to some constant. Okay. XY is equal to constant is an equation of a rectangular hyperbola. You may not know it, but learn from now onwards that xy is equal to some constant graph will look like this, and this is called rectangular hyperbola. Okay, this is the pressure versus volume graph at constant temperature and number of moles. Okay, now if the temperature is increased, See, if the temperature is increased, this constant value will increase, which means pressure into volume value is increasing. Okay, pressure into volume value is increasing. So therefore, I can say that, suppose if the pressure versus volume, if we check it out, as the temperature increases, the P into V value will increase. So the graph will start becoming far away from this origin. So we can say that temperature T3 is greater than T2 is greater than T1. So this is what you will see at different temperatures. Okay, students. Now, in J, instead of directly asking P versus V, there would be a lot of different types of graphs that is being asked. So you should be able to figure out whatever the graph that is given. Suppose, what are the types of graphs that can be asked? First, pressure versus volume. That's pretty easy. We have done it. Second, log P versus log V. Log V. This can be asked. We know that PV is equal to constant. So taking log on both sides, I will get log P plus log V is equal to log K. So log P will be equal to minus log V plus log K, which will replicate the equation of a straight line y is equal to mx plus c, where m is minus 1. You can see that m is minus 1. So which means it is a negative slope. And this is a positive value. So it is a positive y-intercept. So negative slope and positive y-intercept tells us that if you plot log P versus log V, the graph would look something like this. So I hope you understood, all of you. Similarly, okay. Similarly, if you have to plot PV versus P, correct? We know that PV is a constant value. So if you plot it with respect to P, it will always be constant. At any pressure, the P into V will always be constant. The other graph that could be asked is P versus 1 by V. We know that PV is equal to constant. So P will be equal to K by V. So which is same as y is equal to mx. So y is equal to mx is a straight line passing through origin. This is how it would be. So P versus 1 by V. Fifth. Okay. Now these are interesting ones which you need to do, which you have to try. P by V versus 1 by V. Now this is where usually students fumble a bit. Please try this. The other curve which I want you to try is P versus ln V log. Please try these two graphs. And graphs which are plotted at constant pressure, these are plotted at constant pressure. All these graphs are called isobars. So any graph that is plotted at constant pressure is called isobar. Constant temperature is called isotherm. Same way, just like how you have plotted earlier, here also you should be able to plot, but I want you to do this later. Try this on your own. And you can send me on WhatsApp. I'll tell you whether it is correct or not. Vt versus V. Try this. Vt versus T square. Similarly, Vt versus T. You can try T versus ln V. Okay. Please try these graphs later and see how they are varying. Yes, students. Now, questions that would come from this area would be either in terms of how the pressure is related to one another, right? How the temperature is related to one another. The third law will be about Gay-Lussac's law. Gay-Lussac's law. Now this is at constant volume and number of moles. At constant volume and number of moles, pressure is directly related to temperature in kelvins. Everything is same. Here P is equal to some constant into temperature. P1 by P2 is equal to T1 by T2 at constant volume and number of moles. This is Gay-Lussac's law. The graph would be similar as that of what we have learned in isobaric cases, which is pressure versus temperature. We'll get a straight line here. And these are at constant volume. So this is V1, V2, V3. Here also you can apply the same way how we have done it earlier, that if I take constant temperature curve, you can see the pressure is increasing. So if the pressure is increasing, volume must decrease. So V1 should be less than V2 should be less than V3. This is how it is related. Now we call them as isothermal, isobaric. This is called isocores. So three types of graphs: isobars, isotherms, and isocores. Cores means constant volume, bars means constant pressure, therm means constant temperature. This is how the graphs looks like. Okay. Uh, last gas equation is Avogadro's equation or Avogadro's law. Avogadro's law tells us that at constant temperature and pressure, volume is directly proportional to number of moles. It's like inflating a balloon, right? More the number of moles you blow inside, more is the volume that it will occupy, considering the pressure and temperature inside is same. Okay. So which means V is equal to some constant into N, or V1 by V2 is equal to N1 by N2. Right. Now this condition becomes very important to understand something called STP, standard temperature and pressure. Standard temperature and pressure. That is, what has been found that if I take 1 mole of a gas, for 1 mole of a gas, the volume occupied by gas is found to be 22.4 liter at temperature of 273 kelvins, which is nothing but 0 degree centigrade, and pressure being 1 atm. The way to think is like this. Imagine I have a balloon. A completely flat balloon. Then I injected 1 mole of gas into it. Outside pressure, I'm maintaining it as 1 atm. Temperature also I'm maintaining it as 0 degree centigrade. Imagine this all is in one particular room. Then slowly what happens, this gas will expand in this balloon. The gas will expand in the balloon, and a time will come in this room, when this gas is occupying, when the balloon is inflated to a volume of 22.4 liters with 1 atm pressure inside and 0 degree centigrade inside, because now it will become mechanically and thermally at equilibrium. So now you can see it is thermal equilibrium as well as mechanical equilibrium. So now it will stop inflation. So once the inflation has stopped, check out the volume. It would be approximately 22.4 liters. Okay. So that is standard temperature and pressure. Okay. Now standard temperature and pressure as per the new NCRT, because now standards has been changed, that all the pressure standards have changed to 1 bar, which means these are thermodynamic standards. 1 bar, temperature is still 0 degree centigrade or 273 kelvins. In that case, 1 mole of a gas will occupy a volume as 22.7 liters instead of 4 liters. So please check out your questions carefully. Now, since you will be having numerical questions henceforth in your exams, so please be very careful if it is given 1 bar or it is given 1 atm. If it is 1 bar, take volume as 22.7. If it is 1 atm given, then take the volume as 22.4 liters. Okay. New NCRT recommends this one, this STP condition. I hope all of you understood this, guys. Now combining all of these gas laws, see what's happening from Boyle's law. From Boyle's law, we learned that volume is inversely proportional to pressure. From Charles' law, we have learned that volume is directly proportional to temperature in Kelvin scale. And from Avogadro's law, we have learned that volume is directly proportional to number of moles. Imagine if all of them are changing. Pressure, volume, none of them is constant. Then volume will be directly proportional to pressure also, inversely proportional to pressure also, number of moles also, and temperature also. So which means P into V is proportional to N into T. So if I remove the constant, if I remove the proportionality, I will get a constant, and that constant is termed as R. And this R is called the universal gas constant. Universal gas constant. We know the STP condition. Just now we have learned the STP condition from above. That is, if I take 1 atm, temperature for number of moles, volume, all the data of pressure, temperature, number of moles, volume, everything is known. So if I substitute that, I'll get the value of R. That is 1 atm into 22.4 liters divided by 1 mole multiplied by 273 kelvins. So I'll get the answer as 0.0821 atm liter per mole per Kelvin. If I convert these units, atm into pascals, then it will be 0.1.013 into 10 raised to the power of 5. And volume in terms of meter cube, this one will be in meter cube, same 1 mole and 273 kelvins. Then this value turn out to be 8.314 joules per mole per Kelvin. Joules can also be written in terms of calories by dividing this by 4.18. So this would become approximately 2. So approximately 2 calories per mole per Kelvin. So these are the 3 R values which we will be using a lot. Okay. So one is in terms of atmosphere liters per mole per Kelvin. Next, joules per mole, calories per mole. All the thermodynamics related chapters like thermodynamics, thermochemistry, electrochemistry, got it? Even in organic chemistry, we will be using this R value a lot of times, these two. In gaseous state, we'll be dealing with the pressures in ATM. So we'll be using this R value a lot of times. So be aware which R to be used when. Okay, students, I hope you understood what is ideal gas law. So we got this
Or
as,
where did the joule come from? How is volume into pressure equals to joule?
this is Pascal. Pascal is Newton per meter square, right, beta? Volume is meter cube. Okay, so if I cancel this, this is Newton meter. What is Newton meter? Energy, no? Energy is measured in joules.
Okay, got it.
I think all of you understood that. What is PV is equal to nRT? So this PV is equal to nRT is what we call it as ideal gas equation. There are immense number of applications in regards to ideal gas. Okay, so let us see one or two applications here, and then we'll go ahead with problem solving of different types. First, we have to find the temperature in kelvins. Temperature in kelvins, got it? At which 1 mole of an ideal gas, 1 mole of an ideal gas follows the following isotherm. Follows the isotherm. Here, the isotherm is this way. You know what is isotherm? Isotherm means constant temperature. So the graph given is log P versus log V, and it is given this way. And here the unit is also, this entire distance is 1 unit, and this entire distance here also this entire distance is 1 unit. Is 1 unit. Okay, this is how the question is given. Now you need to find out the temperature. The R value is given. R value is given as 0.08. Do this. atm liter per mole per Kelvin. All the hint you need is PV is equal to nRT. That's all you need to know. If you know that, you should be able to do the question. Try this. Finished? Any answers? Ranveer, any answer, beta?
No, sir, trying.
Okay. And now?
Sir, try.
Sure. We have to
Beta.
use the value of log of 0.08.
Log of?
0.08.
I don't think that is essential here. Check again.
Oh,
All I can say is if log k is equal to 1, which means k is 10. You know that, right?
yes, sir.
Check this, guys. See, all we know is PV is equal to nRT. I told you, right? Just take log on both sides, beta. So log P plus log V is equal to log of nRT, right? So I can write log of P is equal to minus log of V plus log of nRT. And you can see it is pretty much clear that the slope is -1, okay? And which is also clear from this because the angle here is 135. Yes, I think you are able to make it out because this side it is same amount, this side it is same amount. So angle has to be 45 here. So then it has to be 135. That's why it is coming as -1. And what is this one? This has to be the y-intercept. The y-intercept value is already given as 1 unit. Therefore, log of nRT is given as 1 unit. So which means nRT is equal to 10 raised to power of 1, which is 10. So T will be equal to 10 by nR. So 10 divided by n is 1 mole given, R is given as 0.08. That's what I gave you. R value is 0.08. So how much this would be? This would be 1000 divided by 8, which is how much? 125 kelvins. Guys, you understood that? How to try it?
Yes, sir.
Okay. Can you do something similar to that question? One more? Yeah, all of you? Okay, try this one. Anyone has a doubt here? Please do ask right now. Very typical JEE question. This is how it will be. Ishan, you got this?
Yes, sir.
Suppose if you have for 2 moles of an ideal gas, 2 moles of an ideal gas, V versus T graph is given, okay, where T is in degree centigrade. Find the pressure of gas in ATM. That's all. Graph given is this way. Volume versus temperature in degree centigrade. And the graph is going this way. And this distance is given as 0.0821. R value is already given in the question as 0.0821. Please do this now. Yes, but right. That is correct. Ranveer, that's right. Others? Check again or no? You can make out this now. PV is equal to nRT. P is equal to nRT by V. Okay. And you can see at T is equal to 273 kelvins, which is 0 degrees centigrade, right? At this temperature, we know what is the volume given, which is 0.0821. That is what you will use, is in liters. So that will be pressure will be number of moles, 2 moles. R is 0.0821 multiplied by temperature 273 divided by volume is given 0.0821. So how much will be the pressure? 546. 546 watt ATM. Check if all of you got that. Yes, Ishan. Okay. Arya, Arno, you got it now? Should we go ahead?
Yes, sir.
Okay. We got the next type of question, which is based on faulty barometer. Suppose if a barometer is given, in which column is inserted here, and the height here is given as, let's say, 5 centimeters, and this is filled with mercury. Then there is again a gap with some gas here. Just take this little bigger. Yeah. So again, there is some gas. The length of this is 25 centimeter. Here there is, some B gas present here. B gas. And this height is again 10 centimeters. Some A gas is present. And here this height is given as 10 centimeters. So it's a faulty barometer. There is a lot of gases stuck inside. Okay. Clear? Outside pressure is P ATM. Pressure in ATM. Now we need to find out pressure of the gas in both the sections. Pressure of gas in A and B. What will be the pressure of gas in A and B? Clear, everyone? Can you try this once? Okay. This ATM pressure is approximately given as 76 centimeters of mercury, just for our convenience. All of you have to calculate what is the pressure of gas A, pressure of gas B, if this kind of a faulty barometer is present. Right, Ranveer. Correct. You have done this type of questions, Ranveer?
Yes, sir. These are the basic types I've done.
Good, good. Arnav, you got that? Yes. Aya?
Sir, I'm still doing.
Observe this. It just requires a simple technique. Usually we miss out on that. Check out. Here we have a column of 10 centimeters. Then we have a B gas. And then we have another column here. Imagine it's like we've been pushed by atmospheric pressure. And that atmospheric pressure is being balanced by this mercury column, which is 5 centimeter. And it is balanced by this gas pressure, pressure of the gas, which is pressure of B gas. And this has no influence. This 10 centimeters mercury has no influence. Why? Because the gas will act equal pressure in all the directions. So the P gas, the pressure of the B gas is also balancing upwards whatever the 10 centimeters that is coming from. I think all of you understood that. Yes, Ansh, right. So therefore, pressure of ATM will be equal to pressure because of this 5 centimeter column plus pressure because of this B. Same way when it comes to upwards here, got it? So you can see there is a pressure acted by air column here, and this is been balanced. So we can say that pressure on column on B gas will be equal to 10 centimeter of Hg column plus pressure of A. Solving this, we will get pressure of A is 60 centimeters and pressure of B is 70 centimeters. I think all of you understood this type, right? So these are very easy ones. So I guess you know how to do these types. Now suppose if at all you have been asked, right, two gases are being mixed together. This is the next type of question. Now here the temperature is maintained at T1, temperature is maintained at T2. Okay, and the number of moles, the volume here is V, volume here is V, both of them are of equal volumes, and number of moles here is N1 and number of moles here is N2 initially, and both of them were in separate chambers. Then as soon as you remove this opener so that gases can intermix with each other, got it? We need to calculate the pressure, final pressure of gas, final pressure of gas in terms of P1 and P1 and P2, considering here pressure is P1 and pressure is P2 here. Okay, P1 and P2 and T1 and T2. You have to calculate the pressure, final pressure in terms of P1, P2, T1, T2. Please try that. Done. Right, Ansh, correct. After that, P final. You can tell me, Ansh. Did you guys get this? So the only thing which you need to check out is whether what is the average final temperature. If that was asked, you can just write out in terms of weighted average. Okay. The final form, how you have to represent, depends upon what is being asked. Suppose if the volume is, if the final pressure is being asked, correct? Now, check out how the number of moles are related with one another. You know, N1 plus N2, it is related in this way. So you will cancel this out and you will have this as N1 T1 plus N2 T2 by RV. This is one final form. You can write in terms of V, or this V is actually V final, right? Which is V1 plus V2. Got it? Sorry, I made a mistake here. So this is V final. Right. So that is V1 plus V2. So you can write either in terms of this V final, depending upon what is being asked, or you can write this as N1 T1 plus N2 T2 divided by R into, because we know V final will be equal to V1 plus V2. Now write everything in terms of V1 plus V2 as a temperature and pressure. So you'll get N1 T1 plus N2 T2 divided by R into, again you will write this as NR T1 by P, P1 plus NR T2. There is no R here. Yeah, there is no R here. So simply V1 plus V2 R is above here, right? Here, R is here. R is here, and you can write this by P2. So we can show it. So if you check out N1 and N2, I can write in terms of nRT PV by T here. So I can write this as both, either you write it in this way, or since both the volumes are same, you can just write down 2 here and take out that. So you will write this in terms of volumes or in terms of number of moles. So if you write in terms of number of moles, this is N1 and N2, got it? So the final expression would be N1 T1 plus N2 T2 divided by N1 T1 by P1 plus N2 T2 by P2. This is writing in terms of number of moles. If you are not, if you have to showcase that in number of moles. If different volumes are given, this is when you have different volumes. Since it is same volumes, this V will be, final V will be 2V, that's all. So which means it will be N1 T1 plus N2 T2 into R divided by 2 into V. N1 I can write it as P into V, P1V by R T1 plus P2V by R T2, that multiplied by R by 2V. So that R and V will get cancelled, and T1 is already there, T2 is already there, that will also get cancelled. So it will simply be P1 plus P2 by 2. Okay. So depending upon however the data is given, either you have to express that in terms of number of moles and temperature if the volumes are different. If the volumes are same, it will simply come as average of these pressures. Got it? Hey guys, you understood that? Now the same type of question, slight modulation. This time what we are doing, we are not changing the temperature in either of the cases. Suppose if this is constantly maintained at a temperature here, if this side is constantly maintained at a temperature, this side it is in a bubble bath, or it is in a bath here, which is constantly maintaining a temperature. This side also there is a bubble bath which is constantly maintaining a temperature T1 and T2, and this is not changing. In that case, if you have N1 and P1 here, N2 and P2 here, now relate what will be the final pressure. This is initial number of moles, temperature, initial number of moles, temperature, and these are the initial pressures. Now minute we open this, you have to ensure that the temperature is always maintained on both the sides. Got it? Now you guys can check out what will be the final pressure. Please let me know. Sorry. In such type of cases, you can always consider some moles of the gas would be moving from left to right or right to left. Okay. Let for our simplicity, I'm assuming that T2 is greater than T1. It doesn't matter whether it is greater than or less than. So imagine some moles of N2 has left towards, N1. So some X moles have moved towards this chamber A and this is chamber B. So some X have been lost. So this new number of moles will be N2 minus X. So we'll have N2 minus X are the number of moles. R into T2 divided by some volume. This will be the volume of, this B here. So let's say this is volume of B. And that would be equal to N1 plus A, N1 plus X into R into T2 divided by VA. Got it? Well, volume I'm always considering it to be the same in both the cases. So in that case, volume will get cancelled. Why I'm equating here? Because since it is open, the pressure here and the pressure here should always be same. Okay, because the minute you open it, the gas will move such a way so that the pressure on both the sides remain constant. That is to achieve the mechanical equilibrium. So once it reaches to the mechanical equilibrium, both of these would be equal. So from here, we can say that N2 T2 minus X T2 is equal to N1 T2. Sorry, this is N1 T1. Okay, plus X T1. So from here, if at all I take X common, T1 plus T2, that will be N2 T2 minus N1 T1. So X will be equal to N2 T2 minus N1 T1 divided by N1 T1 plus T2. So if you substitute this value in here, you should be able to get the pressure. Clear, everybody? Ishan, you understood that?
Yes, sir.
Based on this, there is a simple question that was asked in JE on the same concept. How it is been asked, check it out. He has given something like this. There is a container and it is connected to another container which is vacuum. There is nothing here, so it is vacuum. And number of moles of A is given as 4 here, maintained at 300 kelvins. This is maintained at 600 kelvins. This is 10 liters flask. This is 20 liters container. Okay. Right. So in this case, it is asked what are the final number of moles of A, final number of moles of gas in A and B. Gas in A and B. That is, this is container A and this is container B. This was the question given. Try this, guys. It's a very simple question. You should be able to answer it fast. Yes, correct or no? This is a simple question. I just want to make sure you are in line. Ansh, others just give me an answer if you are getting that. Ranveer, you got that? Okay, Ansh, check. We just have to equate the pressure on both the sides. So NA, you can say this is NA minus X into RT divided by T1 or TA divided by volume A. That should be equal to NB, which is nothing but X here. So I'll write it as X into RTB divided by volume of B. Substitute the values, calculate X from there. So which is 4 minus X into TA, which is 300 divided by 10 is equal to X into 600 divided by 20. So if we calculate X, it will come as 2. So which means eventually you have 2 moles on left hand side, 2 moles on the right hand side. And you understood that?
Yes, sir.
Arya,
Yes, sir.
are you there, beta? Yeah. Ranveer, you got that?
Yes, sir.
Okay, beta. Guys, if you check out, I have uploaded 3 papers here on your group. Ranveer, I'm sending you personally. Check out. Ranveer and Ishan, I'm sending you both personally because you are not on the group, I guess.
Okay, sir.
We have period. I sent you periodic properties, mole concept. There are 2 mole concept sheets. One is on the basis of concentrations, one is on the basis of eudometry. Next one is the structure of atom. All right. So I will point out some questions. I want you to try them first. Okay, guys. Ranveer and Ishan, you must have got that. Check better. Yeah. So you guys will first open structure of atom. These are all previously asked questions in various institutes like Allen or Pace,
Oh.
Sri Chaitanya and so on. Okay, some good questions.
So
Haan beta.
I haven't got it.
Ishan, check now. Let's see to someone else. 922353756. Is that the number?
Oh, that's my mom's number. I'll ask her to send it to me.
Okay, beta. And just put a hi to me so that I can add it to add you to the group, or either I can send you again next time. Yeah.
Okay.
Right, guys. Okay. There are few simple questions, some difficult questions, but more or less you should be able to do all of this. Okay. But currently, right now, we will discuss some things which are, twisted and turns, those questions. First, come to structure of atom. Everyone, go to the second page. I want all of you to try 22 and 24 first. Ansh, Arnav, I hope you got that sheet better.
Yes, sir.
Okay. Arya, did you open?
Yes, sir. I'm open.
Okay, beta. Check out 22nd and 24th first. All of you, first do those two questions. I'll give you 5 minutes, then we can discuss. I'll come in a minute, everyone. Yeah, guys, I'm back. Sorry. I 22 and 23. What does that mean, Arnav? You mean you finished?
No, sir.
Okay. 22, all of you are done? Any doubt there? Yes or no? Just let me know, guys.
Sir, could you solve question 22?
22, beta?
Yes, sir.
Okay.
Yes, sir. Even I didn't.
Okay, no issues. See, the closest distance approach, what you need to check out here, what happening is closest distance is, suppose if there is an alpha ray going for, scattering on the nucleus, say this is the nucleus, got it? But the nucleus, we need to find out it has slightly bigger. So I'm just writing the same nucleus slightly bigger. Imagine this. And now here, as you come, when it comes to this alpha particle, as it travels from here, before it is starting to hit the nucleus, it would have kinetic energy and potential energy is 0. Got it? Potential energy is 0 because at this point, it is too far for having any attraction or repulsions. The minute it approaches this point, where it will come closest to this distance and then it will move back. In here, the kinetic energy, let me call it as Ke2 and potential energy 2. Here kinetic energy will be 0 exactly at this point because the velocity has become 0. But here potential energy will be 0. So I can say kinetic energy at this position will be equal to that of potential energy at this position. So at position A and position B, if you can check it out. How do we calculate the kinetic energy in general? Sorry, potential energy in general. Potential energy will be equal to some constant into the charge. The charge is Z into E, where Z is the uh, atomic number or number of protons, into E is the charge of one proton, into the alpha particle charge, which is 2 proton charge. So 2E divided by the distance. So the closest distance to which the alpha ray is coming, that is called the R minimum. This is the way to calculate the radius of the nucleus. Okay, guys. So that is the R minimum. So this in magnitude should be equal to the kinetic energy. So kinetic energy will be half into mass of alpha particle, speed of alpha particle square, that should be equal to K 2 times of Kz E square by R minimum. So implies R minimum would be equal to 4 times the Kz E square divided by M into V square. So from here, when you are comparing the speeds, as per the question, you are supposed to compare the speeds, right? Which is giving with or without error. So without error, it was V. With error, it is V by 2. So if we consider that, so R minimum, first I'll call it as R1 by R2, that should be equal to V by 2 whole square. So which means R1 should be equal to 4 times of R2. So how much is the difference? That should be the error, right? So the difference is how much, beta? It is R2 minus R1 will be equal to, sorry, R1 minus R2 will be equal to 4 times that of, 3 times that of R2, right? So which means the difference we are getting is almost how much? 3 times. So if you write in terms of percentage, how much it will be? 300%. That is the error which you are getting in measuring the distance R. Guys, have you understood that?
Sir, there it is written in the first experiment speed of particle. That particle is also alpha particle.
What, beta? Does it
In the
matter? I've
second,
just does it matter because I've written it for alpha particle because we do it for Rutherford's experiment. But whether it is any alpha particle, whether it is any particle, R and V will be related this way only, no beta.
okay, sir.
But I've given you this equation so that even if it is directly asked about R minimum, this was a 2009 question, 2000 JE advanced question, where you have to calculate R minimum of copper plus nucleus. So this was something which you can use there. All right. Everybody understood this 22nd question? Okay. 24th. Have you tried or you need time?
Sir, need time.
Okay, try this. It's a very, very good question. I want all of you to do it properly. And I'm expecting hopefully you should get this question in major test. Yeah, Ranveer, check. Ranveer, done?
Yes, sir.
24 guys, come on. कितना स्लो करते हो यार आप लोग? कुछ आंसर दो जल्दी. A C D. Okay, beta. A C D. Others? B C D. B C D. Okay. Only B. Not A. Okay, that is a good way of putting it. Uh, okay. Okay, Shansen, right. Okay, Arno, not A. Right. Okay, so the answer actually is C and D only, correct. Now, why not A? Check this. One thing, while solving these type of questions, you got to understand and remove the duplicacy. Suppose if you have hydrogen, this is 1 to 4. So from 2 to 1, when the transition is done in hydrogen atom, this is helium, this is lithium 2 plus, imagine. So in case of hydrogen, when 2 to 1 happens, it is 13.6 into 1 square into 3 by 4. So I'm writing directly. So you should know what is the energy of the transition. Okay. So energy of this wave, energy of this radiation that is coming out should be 13.6 into 3 by 4 electron volts. Now 2 to 1 transition here, 2 to 1 transition here. Now compare that with 4 to 2 transition here. This is 4, 3, 2, 1. 4 to 2 transition here. So what do I get? 13.6 into helium is 2 square into 1 by 1 square, 1 by 2 square minus 1 by 4 square. That is 13.6 into again 3 by 4. Check this. Right, Arya, correct. So from 6, 5, 4, 3, 2, 1. Again, from 6 to 3, check out in lithium. So it would be 13.6 into 3 square into 1 by 3 square minus 1 by 6 square. So how much you are getting? 13.6 into again 3 by 4. Could you see any pattern here? So 2 to 1 transition of hydrogen would be same as 4 to 2, then 6 to 3 and 8 to 4 and so on. Is this clear, guys? So this is a pattern. So now when you calculate the total transitions coming from 4 to 1, so 4 to 1 here means n into n minus 1 by 2, so which is 4 minus 3 by 2, which is 6 spectral lines you are expected here. N into n minus 1 by 2, here 15 spectral lines are expected. So total spectral lines will be 21 is what you are expecting. But point is, out of this 21, one is common because this spectral line has same energy, which means this is the same spectral line that is coming here. Okay, so these two spectral lines are same. So subtract 1. So what should be the total number of spectral lines? It should be 20. Rest all them, it don't match. Okay, you don't have to worry about checking again and again. It won't match. All of them will be different only. I think all of you understood this point. Next, more than 10 lines are in UV range. Okay, UV is the case when you have Lyman series, which means in hydrogen, if it is falling from 4 to 1. So 4 to 1, how many are falling here now? I mean, sorry, anything higher to 1. So how many we are getting here? In this case, we will get, we will get 4 to 1, 3 to 1, 2 to 1. So these three are definitely falling in Lyman series. And out of this 20, you can see 6 to 3, if 6 to 3 is Lyman series, because this will also be seen in UV rays only because this is the same radiation as what you are getting here. So which means if this is 6 to 3 is 13.6 into 3 by 4, can you just check out what would be 13.6 into 5 to 2? Can you check out 5 to 3 here? Right, sorry, 5 to 2 here. If you check out 5 to 2, you will see it is 1 by 2 square minus 1 by 5 square, right, into 9 here, right? So 13.6 into 1 by 4 minus 1 by 25. So that is 21 by 100, which is 25 by 100 multiplied by 9. Okay. So even if you take, this is approximately 10 and cancel it, it is coming almost like 2 times. Got it? Which means this is more than this. what happens if you check out the transitions from higher 6 to 3, if you compare with 5 to 4, 5 to 2, 5 to 2 will have more energy. Similarly, 4 to will have more energy. Okay, same way if you check out 2 to 1 will also have, you know, more energy, because transition would be, the transition energy would be more. So usually you would see that if 6 to 3 is happening, then 5 to 3 or 4 to 1, they would also have more energy in this case. I hope you guys understood that. Yeah. Now just like here, when it is 2 to 1 is also Lyman, 3 to 1 is also Lyman, 4 to 1 is also Lyman. So these are, you can see 2 to 1 is least energy, 3 to 1 is slightly more, 4 to 1 is more. So anything which is more than this energy will also lie in the UV rays. So you can see 4 to 1 it is coming, correct? So all of them into 9 you have to multiply. So they all will be more than this only. More than this only. Everyone? So 4 to 1, how many? You will have 6 of them. Similarly, 5 to 2, you'll have, this one will be 7 of them, 8, 9, 10, 11. So we will get at least 11. All of you understood this? Correct. So definitely more than 10 lines are being observed in UV range. Next, if sample contains only 10 atoms, then emission spectrum contains only 2 visible regions. Visible region is when you have jump towards n is equal to 2. So you can see 4 to 2, 3 to 2, only 2 Balmer lines. So only C and D are correct. I think all of you understood that. Ishan, is this clear?
Yes, sir.
Arnav?
Yes, sir.
Okay. Okay, I want all of you to try 26 now. 26, 27. Let me know once you finish 26. Give me an answer if you have done. Yes, Ranveer, that's correct, beta. So you got all the answers? Very good. Others, Ansh, did you got any answer, beta? Okay. Yeah.
Yes, sir.
Okay. Did you check out D, beta? Ansh, can you check out D option again?
Yes, sir. I'll check that.
Hmm.
It's done. I'm not cutting anymore. No, it's not coming. I'm just removing the dirt. See.
Arnaud, can you check out C, beta?
You know who's Wally Frank? Wally Frank. The meat flea.
Ishan, you got that?
Doing it, sir.
Arnaud, check 27D. D once again.
Yes, sir.
Okay, we'll leave that. Leave that. That is done. Okay? We'll go to next meeting.
अरे ऐसा नहीं कर.
अभी done हुआ होगा.
Arya, are you getting 26 AC, beta? I think B should also come. Check.
Is that fine?
Okay. So radius of second excited state of lithium. Second excited state as in n is equal to 3. If you are getting confused there, should be n is equal to 3. And here we got two things. V naught is equal to 2V. R naught is equal to x by 4. Use that for fundamental here. So radius of third orbit is equal to R naught Z R naught n square by Z. This is the general formula. R naught is equal to x by 4 into n square, which is 3 square divided by 3. So 1 3 will get cancelled. Correct? So x R n lithium second excited state, n square divided by z. So r3 radius of orbit is not is equal to x by 4. So A is not coming, beta. Why A is coming? Check. So you're only getting 3x by 4, not 9x by 4. So A should not come. Yes, correct. So B should be right. B is coming for sure. C is also coming. Check that. So time period will be, 2 pi r divided by V. Correct. So 2 pi into r we just got as 3x by 4, and V, third velocity in the third orbit, that will be r naught z, sorry, V naught z by n, V naught z by n. So V naught we already got it as 2y, z is 3, n is 3. So 3 will get cancelled. So that will be 2y. Okay. So this 2 will get cancelled. So 3 pi x by 4y. So that is coming. Yes, correct. Yeah, now I think all of you got that. Ishan, you understood that beta?
Yes, sir.
27. 27. Faster, guys. Taking a lot of time. What time is the exam tomorrow?
3 o'clock.
3 o'clock. Okay, you have time to finish this. Chalo. Even B, that was for the earlier question, Arya.
Yes, sir.
Give me an answer for 27. Okay, Ansh has got it. Ansh, come to page number 7. D part beta. Okay, I'll show you. Ranveer, 1 minute. Those who have finished 27 also, Ansh, if you have finished, then go for page number 7, question number 24.
Okay, sir.
Okay, now check this D part. Ranveer, check the D part beta. See, in fact, any form of energy will always depend upon some constant into z square by n square. So potential energy would be equal to, now he's written in terms of mass of electron, correct? Usually when you write potential energy, we know that potential energy is half of the kinetic energy, because magnitude wise, I'm writing magnitude wise. So which is half into m into v square beta. Clear? So that would be half into, sorry, one more half. So that will be 1 by 4 times of mass into v square. Ranveer, you know why potential energy is half times of k kinetic energy?
Yes, sir.
Okay. So use that fundamental beta. So 1 by 4 into mass of electron into, now we need to calculate potential energy for second excited state of lithium. So therefore n is equal to 3. So this is for Vn. Vn is V naught Z by n. So 3 by 3. So that will get cancelled. Okay, beta? Got the answer?
Yes, sir.
This question has been repeatedly asked in your majors a lot of times. So remember this question. 27, you got it? All of you? Ranveer, did you finish 27?
Yes, sir.
Okay, then go for 24th. Others? Arya, Ansh. Ansh has done. Arya, Ishan,
Sir, I'm still solving.
do it fast, beta. Let me know. Arnav?
Done, sir.
Okay. '27, you are not getting D, Ishan.
No, sir. I was saying it won't be D.
24th, in the next sheet, in the same thing, page number 7, Ranveer. Because these are something which we have discussed. 24 is something which is new question.
Sir, actually, I didn't understand the notation only
Which one?
in the 24th one.
This one? Notation.
Yes, sir.
Psi of 3 to 1 represents n is equal to 3, L is equal to 2, and ML is equal to 1. Okay.
Oh, okay, sir.
Right, Arnav? That's right. Arnav, come to page number 12. Do 32, 33. Others, do 32, 33. Page number 12. Yes, Arya, correct. Ansh, correct. Ranveer, correct. 24th is correct. Come to question number 32 and 33 of page 12. Ishan, if you have stuck, just you let me know, okay? Finish 24th first, Ishan. Others, please come to question number 32 and 32 and 33, page 12. No, correct beta. Go for the next one. Okay, everyone, I think all of you got 32. 32 except now anybody else who has got answers for 32 or any doubt in that?
Sir, I have doubt regarding Z component.
Z component.
Yes.
Okay, the maximum Z component of the orbital momentum. Okay. The H star which you see that, right, beta, which means it is H by 2 pi, you know that, right?
Yes, sir.
Yeah. So if you know, when it comes to orbital angular momentum, orbital angular momentum here, OLM, that will be under root of L into L plus 2 H by 2 pi, correct? Right, beta?
Yes.
Okay. So in that case, what will be the L value here? For L is equal to 2, how much that will be angular momentum? This is L into L plus 1, sorry.
Root H1.
Hmm? This is root
6H by 2 pi.
6H by 2 pi, right? Now, what is this Z component? The maximum Z component of orbital angular momentum is 2H. Uh, One second, beta. I'm trying to load the diagram so it will become easy for you to understand. Okay. Listen up. I'm not able to load it. Check it out. Suppose when you have the Z component here, see, normally all the ML values represents the orientation. Okay. So if ML value is 0, so this is taken as the reference with respect to that, this being the angle theta, that gives how does the dz square looks like. This is how the dz square looks like. Okay, beta. Now in here, the angular momentum with respect to ml is equal to 0, that would go in this direction, orbital angular momentum, which is represented as Lz. And this Lz, I would rather suggest you remember like a formula as ml into h by 2 pi, whatever the magnetic momentum of that, which is L into cos theta. This is where it comes from. All right. So if you check out their orientation above and below at theta is equal to 0, right? Because Lz will come when theta is equal to 0. How much that would be, beta? It will be h by 2 pi above and minus h by 2 pi below.
Yes.
Is this clear, beta? Right. So the question asked here is, where is that? Yeah, the question asked here is for L is equal to 2, the maximum Z component of the orbital will be how much? Correct? 2 times of h by 2 pi, which is nothing but, what is the maximum amount which you will have, beta?
H by
This
pi.
h by pi, h by 2 pi plus h by 2 pi. So that will be h by pi. Okay. And next one, the number of allowed values of L depends upon N and N as well as ML. Is that correct? 32. Somebody has written D. That's not right now, but it only depends upon N, not ML. 32. Check out 32. 32B. Okay. Knowing precisely all the components of non-zero angular momentum of electron in a hydrogen atom would violate Heisenberg's uncertainty principle. Is it true? Anyone? Arnav?
I think it is false.
Why, beta?
Sir, because Heisenberg principle states key it states a relation between the position and the velocity. So I think we can remove the velocity.
We
Oh
can?
no, sorry, it's momentum, right? So that's
Yes.
no, no. Still, I think it's false because it tells us a relationship between the velocity and the position. But here they are only talking about momentum, which only has the velocity factor in it. So I don't think it will violate Heisenberg's principle.
Correct. Okay. Next, C. S orbital has angular independence. That is, S orbital wave function is independent of theta and phi. Is it correct? Yes, beta, it is correct, because when it comes to psi value of any S, whether it is 1s, 2s, any ns, you will get k e raised to power of k dash r into functional n minus l minus 1. R raised to power r won't be there. This will be 0. And all this sine theta cos theta doesn't, it won't depend upon theta and phi, because at every theta and phi, you will see orbital will exist. That means probability will exist. Nodes are 0. Angular nodes are 0. So that is correct, beta. It is independent of theta and phi.
Okay, sir.
Okay, last one. In radial distribution function, n is the number of wave functions changing its sign. The number of radial nodes for that orbital is n plus 1. Is this correct? No. Number of radial nodes will be how much? N minus L minus 1. Yeah. Clear on that?
Sir, so in 33, A will be correct or wrong?
A will be wrong, beta. Okay, so that is wrong actually. I made it false. So it should be B and C, everybody. All of you got that? Yes, Ranveer, you're right. Correct. Okay, I will take few questions. Please try to do B and C also is correct. Ranveer, 33, B and C is also correct. Check. It is
Okay, sir.
independent of theta and phi. Yeah. Now, please finish these questions. These are very selective ones, whatever I have taken in structure of atom ones. Finish this. You have sufficient time now. Whenever you get time, just do this. Now come to the next sheet, which I have sent you. I'll tell you which questions you have to do. At least finish that, and you can at least post me on WhatsApp. See, mole concept question bank 2, SMT question bank 2. Check. The paragraph is very good. Please make sure you finish that. It's a very good, tricky and very nicely made paragraph. Do that. Paragraph question number 3 to 5. Everyone, are you making a note of it? 3 to 5 you have to do. Okay. Next, like these are expected ones, okay? Minimum I'm expecting this you will do. Next, integer type 2 and 3, very good questions. These are the types that have been asked earlier, okay? Everyone, integer type 3 and 5, sorry, 2 and 3. Okay, so you have total of 5 questions which are must do from this one. Have you been taught what is a free percentage oleum or free SO3 already?
No, sir.
No, okay, then don't worry about that question. Next, come to eudiometry. Everyone, eudiometry. Eudiometry, I would suggest do questions from 5 to 9, all of them. 5 to 9. All are good questions. And last paragraph, 15th. And 15th paragraph. 5 to 9 and last paragraph, 15th. Please try these questions. These are some good questions which you can do it for eudiometry. Lastly, you don't have eudiometry. Oh, that's wonderful. Then don't worry about eudiometry if you don't have it. If you don't have eudiometry in syllabus, don't worry about that sheet, okay? Right now, at least. Periodic properties, I would strictly suggest try all of them. They are all very, very good questions. Okay, 20 questions are there. It's a very good test paper. So I would suggest all of you to do that. No questions to be skipped. All of them must be tried. Okay, students, you finish this and make sure you clear all your doubts by tomorrow afternoon before the exam. Okay, you can post me in the morning tomorrow so I can clear that up. Okay, but please try these questions, everyone.
Okay, sir.
Okay, sir.
Yeah, okay, I'll end the session now. So if you have any doubts, you can please post me on WhatsApp, everyone.